The objectives for this module are to understand fuzzy logic, understand what is fuzzification, and describe fuzzy neural networks. Fuzzy logic. Definition of fuzzy. Fuzzy is something that is not clear, distinct, or precise, or blurred. Definition of fuzzy logic. A form of knowledge representation suitable for notions that cannot be defined precisely, but which depend upon their context. For example, in the case of uh, Boolean logic or binary truth table logic, we had variables that had the value precisely 0 and 1. But in fuzzy logic, variables can have values between 0 and 1 in form of decimals that may belong to the either set of crisp set of 0 or 1. So fuzzy means unclear. So it will be unclear whether that variable belongs to the 0 set or the 1 set, but based on some rules we can classify them as 0 or 1 based on their fuzzy value. So fuzzy values can be between 0 and 1 for this case of Boolean logic. Now we move on to logic operations. So before that I'll clear what is meant by truth of x here. Truth of x is the fuzzy value I was talking in previous slide. That will be a decimal value mostly. So it ranges from 0 to 1, and which will be a decimal value, for example 0.75. So since this is more near to 1 value, we can take this value finally to be 1 when considering the final output of applying it to the logic. But if we want to calculate negation of x, that will be 1 minus truth of x. So that will be 0.25 here, because truth x is equal to 0.75. So similarly, for x and y, we have minimum of truth x and truth y. So the minimum of, suppose two fuzzy variables are given as x and y, then truth x and truth y imply the fuzzy values of truth, sorry, x and y, and the minimum of that will be the x and y of those fuzzy values. Similarly, x or y of two fuzzy variables x and y will be the maximum of truth of x and truth of y, and x subset of y will be maximum of minimum of truth x, truth y, and 1 minus truth x. Crisp sets. In a crisp set, members belong to the group identified by the set. For example, slow is equal to s such that s varies from 0 to 50 all inclusive, and fast is equal to s such that s varies from 50 to 70 not inclusive 50 and 70. So in this case 50.1 belongs to set fast, hence 50.1 is not slow. Drawback of crisp sets. Suppose a physical system has to apply brakes if the speed of the vehicle is fast and release the brake if the speed is slow. If the speed is in the interval 49 to 51, such a system would continuously keep jerking, which is not desired. So if the speed of the vehicle is 49, the system will apply the accelerator. I mean, it will speed up and release the brake. And as soon as the speed becomes 51, it will apply brakes, and the speed again will become 49. And so the value will keep variating from 49 to 51. Such a system would continuously keep jerking, which is not desired. Fuzzy sets. To lessen the complexity of comprehension, vagueness is introduced in crisp sets. Fuzzy set contains elements. Each element signifies a degree or grade of membership to a fuzzy aspect. Membership values denote the sense of belonging of a member of a crisp set to a fuzzy set. So fuzzy sets contain elements or variables. Each element signifies the degree or grade of membership to a fuzzy aspect. So that is a each variable signifies that fuzzy value I was talking about. That is the membership value, which denotes the sense of belonging of a member of a crisp set to a fuzzy set. So mapping is done from fuzzy set to crisp set. Now suppose we are given a table on the right side where we have the age as the first column, and these are six categories of people based on the age. So given an age value, suppose 4 here, what will be the membership value for each of these classes? Infant, child, adolescent, young adult and old. These are given in this table. So consider a quiz set A with elements representing ages of a set of people in years. Let A is equal to 2, 4, 10, 15, 20, 30, 35, 40, 45, 60 and 70. Classify the age in terms of 6 fuzzy variables or names given to fuzzy sets as infant, child, adolescent, adult, young and old. So given this set A, we have to classify all the elements as either infant, child, adolescent, young adult and old and give their fuzzy set membership values. So membership is different from probabilities. Probability is different from membership values. Memberships do not necessarily add up to 1. That is the most important thing. So as discussed earlier, the table shows the fuzzy sets ages: infant, child, adolescent, young and old. The values in the table indicate the memberships to the fuzzy sets. So these are the fuzzy sets of ages that are infant, child, adolescent, young adult and old, and the values in this table are, for example, the membership values in this set, fuzzy set. For example, consider the fuzzy set child. A child with age 4 belongs to the fuzzy set child with 0.5 membership value here, and a child with age 10 is 100% member. So for age 10, the value of child is 1. So as I told, the membership value varies from 0 to 1. So this is a 100% member of said child, the age of 10 that is. How to categorize a person with age 30? So given this table, a person with age 30 is 60% young and 100% adult. So these are the fuzzy values for age 30. Young is 0.6 and old is 0.3 and adult is 1. So at age 30 it is 100% adult and 60% young. A person with age 40 is old. That is the question here. So what is the age 40? And the old column is here. So it is 40% old only and 40% young, but 100% adult. So that is the answer. Similarly, a person with age 60 is 100% adult and 80% old and so on. So from the table we can deduce the membership values and identify fuzzy values and map to our crisp set. Features of fuzzy sets. A complex nonlinear input-output relation is represented as a combination of simple input-output relations. The simple input-output relation is described in each rule. The system output from one rule to the next rule area gradually changes, not instantaneously. So, given a complex nonlinear input-output relation, we specify a simple input-output relation in each rule by a set of rules, that is, and the system output from one rule area to the next rule area gradually changes. Gradually changes means not instantaneously. So when we are given a set of crisp no set, then when we convert it to fuzzy set, uh, the boundaries change gradually. That is, when we move from one rule to the next rule, it happens not instantaneously but gradually. Some fuzzy terminology. Universe of discourse. The range of all possible values that comprise the input to the fuzzy system. Fuzzy set. A set that has members with membership values in the interval 0 to 1. Membership function. It is the basis of a fuzzy set. The membership function of the set A is given by UA such that U varies from 0 to 1. It stores the if then. The knowledge base is the if then do storer, which is provided by experts. Inference engine. It simulates the human reasoning process by the making fuzzy inference on the inputs and if then rules. So the knowledge base is the basis of converting crisp set to fuzzy set, and the inference engine does that conversion by simulating the human reasoning process and making fuzzy inference on the inputs and the if then rules. Then the defuzzification module does the opposite of what the inference engine does. It transforms the fuzzy set obtained by the inference engine into a crisp value or crisp set value. Engine looks like this. Crisp input is applied to the fuzzy engine. First goes it into the fuzzifier, which creates a fuzzy input set, and it is passed to the intelligence, which based on some rules gives us the fuzzy output set, which is passed to the defuzzifier, which gives us the crisp output. Now I will discuss the fuzzy set operations, union, intersection and complement. The membership function of the union of two fuzzy sets A and B is specified as the maximum of the two individuals' membership functions. It is equivalent to the Boolean OR operation. U A union B is equal to max of UA or UB. The membership function of the intersection of two fuzzy sets A and B is described as the minimum of the two individual membership functions. It is the equivalent to the Boolean AND operation. UA and B is equal to minimum of UA and UB. Complement. The membership function of the complement of a fuzzy set is A is defined as the negation of the specified membership function and is equivalent to the Boolean NOT operation. New A complement is equal to 1 minus UA. In this slide, you see the example of a fuzzy logic system in use. So there is an air conditioner in a room, and the target temperature is the input to the fuzzy logic system, and based on the room temperature, it will do the commands heat, cool, or no change. So basically, based on the target temperature crisp set, it will output the heat, cool, or no change command. Now we will discuss fuzzification. The fuzzifier that performs the mapping of the membership values of the input parameters, temperature and fan speed to the respective fuzzy regions is known as fuzzification. So the fuzzifier basically converts the crisp set into fuzzy set, and in this example of air conditioner, it maps the membership values of the input parameter, temperature and fan speed to the respective fuzzy regions, and it is known as fuzzification in this case. This is the most important step in fuzzy systems. So fuzzification is the most important step in fuzzy systems. Following are the important membership functions. So membership can be calculated based on these three functions: triangular function, trapezoidal function, and Gaussian function. We will discuss each of them now. Function. Triangular function is defined by a lower limit a, an upper limit c, and a value b where b lies between a and c, not inclusive. And the triangular function mu a is defined as on x is defined as 0 if x less than equal to a. So here this case is x less than a. X minus a upon b minus a if x is lying between a and b, including b and not x excluding a, I mean. So this is the case where x lies between b and a. So this is defined as a slope, this slope. Similarly, the opposite slope, that is if x lies between b and c, it becomes c minus x by c minus b, which is this line here. So this becomes a triangle thus, and it is 0 if x greater than equal to c. So x is the input crisp set, and mu a is the output of this triangular function that gives us the fuzzy value or membership value for that x. The trapezoidal function. Trapezoidal function is defined by a lower limit a, an upper limit d, a lower limit b, and an upper support limit c, where a less than b less than c less than d. So they lie on a straight line from left to right. So it is defined as 0 if x less than a or x greater than d. So on the extremes it is 0. But if x lies between a and b inclusive, it is x minus a by b minus a, this slope. If it lies between b and c not inclusive both, then it is 1. And if it lies between c and d inclusive, then it is c minus x by c minus b, that is this slope here. So this is our trapezoidal function. So last one is the Gaussian function. It is defined by a central value b and a standard deviation k greater than 0. The smaller the k is, the narrower the bell is. So smaller the k, the narrower, means it will become like small k is much smaller, then it will become like this, narrower. This is the bell. So it is given as e to the power minus of x minus b whole square divided by 2k square. So this is the Gaussian function. Hope this is clear. Defuzzification. The fuzzy outputs low positive, positive and high positive are to be converted to a single crisp value that is provided to the fuzzy cooler system. This process is called defuzzification, that is converting to crisp set from a fuzzy set. The most common methods are the center of gravity method, the composite maxima method. The centroid of a two-dimensional shape X is the intersection of all straight lines that divide X into two parts of equal moment about the line or the average of all points of X. So that is the center of gravity method. Moment is a quantitative measure of the shape of the set of points. The other step we can do for method is composite maxima method. Steps in fuzzy logic based systems are formulating fuzzy regions. First we have to decide on which fuzzy regions we need to act on, then apply the fuzzy rules, then embed a defuzzification procedure in our model. So this will be the fuzzy logic based system functioning steps. In defuzzification procedure, depending on the application, either the center of gravity or the composite maxima is found to obtain the crisp output. Now we'll discuss the limitations of a fuzzy system. Fuzzy systems lack the capability of machine learning as well as neural network type pattern recognition. So basically we cannot train our fuzzy systems on input data set. It lacks those features. Verification and validation of a fuzzy knowledge based system require extensive testing and with hardware. Basically, we need to have a lot of hardware and do a lot of testing in order to verify and validate fuzzy knowledge based system which has its own rules and models. So third one is determining exact fuzzy rules and membership functions is a hard task and mostly to be done manually. So someone has to program all the fuzzy rules and membership functions calculations manually, and it is mostly done by the programmer and it is a hard task thus. Finally, step 4 is stability is an important concern for fuzzy control. If stability is not found in the fuzzy system, it is of no use. Few applications of fuzzy logic systems are automatic control systems, prediction, diagnostic and advisory systems, user interface and neural language processing, domestic appliances and embedded systems, soft computing and hybrid systems with artificial neural networks, very large scale integrated circuits, microcontroller, fuzzy expert system and fuzzy inference. Fuzzy neural networks. Fuzzy logic systems with imprecise information are good at explaining their decisions, but they cannot automatically acquire the rules they use to make those decisions. A neuro-fuzzy system is represented by a specially three-layer feed-forward neural network. So in this neural network, we have the input layer, the hidden layer, and the output layer, and basically they learn the rules that take decisions on fuzzy logic. The characteristics of fuzzy neural networks are discussed now. Compared to a common neural network, connection weights and propagation and activation functions of fuzzy neural networks differ a lot. So the connection weights and propagation and activation functions of fuzzy neural networks change from the regular neural networks. Although there are many different approaches to model a fuzzy neural network, most of them agree on certain characteristics such as the following. A neuro-fuzzy system based on an underlying fuzzy system is trained by means of a data-driven learning method derived from neural network theory. This heuristic only takes into account local information to cause local changes in the fundamental fuzzy system. So the fuzzy system neural network is based on the underlying fuzzy logic by means of a data-driven learning method derived from neural network theory. So it is based on neural network only. But this heuristic only takes into account local information to cause local changes in the fundamental fuzzy system. It can be represented as a set of fuzzy rules at any time of the learning process, that is before, during and after. So as I discussed earlier, the input mapping to the output in neural networks is hard, but in case of fuzzy logic neural networks, it can be represented as a set of fuzzy rules at any time of the learning process, that is before, during and after. Thus, the system might be initiated with or without prior knowledge in terms of fuzzy rules. The learning procedure is constrained to ensure the semantic properties of the underlying fuzzy system. A neuro-fuzzy system approximates an n-dimensional unknown function which is partly represented by training examples. Fuzzy rules can thus be interpreted as vague prototypes of the training data. So whatever training data we give to the network, fuzzy rules can be interpreted as vague prototypes of them, and a neuro-fuzzy system approximates an n-dimensional unknown function which is partly represented by training examples. So whatever the training examples we give, fuzzy system approximates an n-dimensional unknown function using that. And first one is the learning procedure is constrained to ensure the semantic properties of the underlying fuzzy system. So basically the fuzzy system is bound in its limits in the input set consideration. So third one is a neuro-fuzzy system is represented as a special three-layer feed-forward neural network as it is shown in the figure. The first layer corresponds to the input variable, the second layer symbolizes the fuzzy rules, the third layer represents the output variables, and the fuzzy sets are converted as fuzzy connection weights. This is the most important. Fuzzy sets are converted as fuzzy connection weights. So weights are the fuzzy connection weights. Weights are fuzzy, that is, and some approaches use 5 layers where the fuzzy sets are encoded in the units of the second and fourth layer respectively. However, these models can be transformed into a 3-layer architecture. So basically, it is the same figure that I showed in before few slides. So it says that first layer is the set of input variables, the second layer is the fuzzy rules, and the third layer represents the output variables. Fuzzy model of artificial neuron can be constructed by using fuzzy operations at single neuron level. So here the summation function is as usual done on the weights and inputs of the input node of the neural network, fuzzy neural network, that is, and then we apply y is equal to g of wx, that is the activation function differently. So instead of weighted sum of inputs, more general aggregation function is used. So instead of the general summation function, we use some other aggregation functions such as fuzzy union, fuzzy intersection, or S norms and T norms for the weighted input to an artificial neuron. So these union and intersection of functions of the fuzzy logic can be used as the aggregator function here. That is cap of xk is implies cap of y. So any excitation in any of the inputs will cause the output to excite. Issue of inhibitory negative weights observes a short digression. In the realm of fuzzy sets, operations are defined in 0 and 1, in between them I mean, or inclusive. Proper solution to make a weighted input inhibitory is to make fuzzy complement of the excitatory membership value. Complement x is equal to 1 minus x. So to make the weighted input inhibitory, that is to make the fuzzy complement of the excitatory membership value, we do complement of x. Input x is equal to x1 to xn is extended to x is equal to x1 to xn, and then complement of x1 x2 up to complement of xn. I mean complement of x1 complement of x2 up to complement of xn. So this is also taken into the input set. The weighted inputs xi into wi, where in between there is an o here. O is a T norm and T conorm can be general fuzzy relations too. So there are specific types of fuzzy neural fuzzy logic functions or relations, and not just simple products as in standard neurons. So the transfer function G can be a nonlinear such as a sigmoid. Transfer function G is also linear at times generally. If wk is equal to 0, then wk and xk is equal to 0, while if wk is equal to 1, then wk and xk is equal to xk independent of wk. So this basically shows the aggregator function used here is OR, and it simply works like this. So basically the output is from 0 to 1 is shown here, and this is the w, and this is x, which is an n vector, n-dimensional vector. Then y is finally OR operation result from x1 and w1, x2 and w2, and so on. And fuzzy neuron. In the generalized forms based on T norms, operators other than min and max can be used, such as algebraic and bounded products and sums. So this is the AND aggregator used here. So this is the output y here, and again, and instead of AND here we use OR. Learning in fuzzy neural networks. Supervised learning in fuzzy neural networks consists in modifying their connection weights in such a manner that an error measure is progressively reduced. So, supervised learning in fuzzy neural networks implies that we modify the connection weights in such a manner that error is progressively reduced. Its performance should remain acceptable when it is presented with new data. So, even when we present new data to the neural network, its performance should remain acceptable. Set of training data pairs xk dk for k is equal to 1 to n are given. Wt plus 1 is equal to Wt plus del Wt, where weight change del Wt is a given function of difference between the target response and calculated node output y. So xk dk are a set of inputs and outputs given for k is equal to 1 to n, and every time we calculate del or the del Wt, where that del Wt is the weight change in and it is a given function of difference between the target response D and calculated node output Y. Y is the calculated node output. Del Wt is equal to f of modulo of dt minus yt. So f is a function here. Mean square error E is my measure of how well the fuzzy network maps input data into the corresponding output, and it is given as half of summation dk minus yk whole square, as here. Similarly, we can use the gradient descent algorithm in fuzzy neural networks as well, using the learning rate eta. We can change it. We can change del w accordingly. Now we'll see some types of fuzzy neural networks, or specifically cooperative fuzzy neural network. So, in the case of cooperative neural fuzzy systems, both artificial neural network and fuzzy systems work independently from each other. So, the artificial neural network is independent of the fuzzy system. The artificial neural network tries to learn the parameters from the fuzzy system, and this can be either performed offline or online while the fuzzy system is applied. Figure above depicts four kinds of cooperative fuzzy neural networks. We will discuss each of them. The upper left fuzzy neural network learns fuzzy set from given training data. So this is the one being considered now. This is usually performed by fitting membership functions with a neural network. So this neural network learns fuzzy set from given training data. Training data is given to the neural network and it learns the fuzzy sets rules. So this is done by performed fitting membership functions with a neural network. So membership functions are applied to this neural net to output the fuzzy sets. The fuzzy sets are then determined offline. They are then utilized to form the fuzzy system by fuzzy rules that are given and which are not learned as well. So offline, this fuzzy system learns the fuzzy sets or rules and gives the output. And the upper right neuron fuzzy system, this one here, determines fuzzy rules from training data by a neural network. So here as well, the neural network learns offline before the fuzzy system is initialized. The rule learning usually is done by clustering on self-organizing feature maps. It is also possible to apply fuzzy clustering methods to obtain rules. So it also performs offline work on fuzzy systems. In the lower left neurofuzzy model, the system learns all membership functions parameters online, that is, while the system is applied. Thus, initially fuzzy rules and membership functions must be defined beforehand. Moreover, the error has to be measured in order to improve and guide the learning step. So this is the neural network. It computes the fuzzy sets and rules and passes to the fuzzy system, and then it calculates the error computation and again updates weights and moves on to the neural net. So this is all online. The lower right one determines rule weights for all fuzzy rules by a neural network. This can be done online and offline. So this neural net here determines the rule weights for all uh, fuzzy rules of this neural network, and a rule weight is interpreted as the influence of a rule. So this is clear. They are multiplied with the rule output. So this neural network calculates the rule weights, passes on to the fuzzy system, and it does the error computation, and it passes to the neural net. Hybrid fuzzy neural network. Hybrid neurofuzzy systems are homogeneous and usually resemble neural networks. Here, the fuzzy system is interpreted as a special kind of neural network. The advantages of such hybrid NFS is its architecture. Since both fuzzy system and neural network do not have to communicate anymore with each other, they are one fully fused entity. These systems can learn offline and online. Figure above shows such a hybrid fuzzy neural network. So this is a hybrid fuzzy neural network. This is a set of rules inbuilt in the neural network on based on nodes, neurons that is, and input is given, and it passes to the neuron. It determines the error. Given the control output passes to the fuzzy system here, and again give the error, and it moves on to give the output finally.